Welcome to Ready to Derive. In this video, we're going to learn to do operations with square roots, adding, subtracting, multiplying, dividing, simplifying, and rationalizing the denominator. Now, why do square roots come about? Let's see some equations that we could solve and how we solve them. So if we want to solve this equation, I know it's very basic, but we would subtract 2 from both sides because we are undoing the operation of 2 being added to x. Similarly, in this case, we would add 2 to both sides. What about if we had 2x equals 10? Well, to undo that 2, we would divide both sides by 2. And if we had a situation where x was being divided by 2, we'd multiply both sides by 2, which we can all do kind of in our heads, right, mentally. But what happens if you get something like x squared equals 10? How does that x and that 2 interact, and how do we undo the 2? Well, we know that the inverse of squaring is square rooting. So we pop couple of square roots on there. But what does that achieve? It basically tells us that x equals square root of 10. So we still don't know what that is. Unlike the other equations which we could solve mentally, this we don't know the answer to. It might be about 3 and a bit, but anything that we figure out, we'll use a calculator, would be an approximation. This is an exact answer, the square root of 10, and we are going to learn how to operate with such expressions. So without further ado, let's get started. So before we get started with the nitty-gritties of operations with square roots, we have to cover 2 very important properties of square roots. We're going to use examples to verify these, and they should be pretty intuitive, but let's pretend that A was 9 and B was 4. So we can do order of operations and work that out to be 36, and the square root of 36 is 6. And let's see if this is equivalent to the square root of 9 times the square root of 4. Square root of 9 is 3, square root of 4 is 2, and that makes 6. Yes, that works. Well, so what it's basically saying is that the square root of a product of 2 numbers is the same as the product of the square roots. And not surprisingly, this is also true when you're dealing with quotients, when you're dividing. So let's take A as 36 this time, and B is 9. So the left-hand side works out to be the square root of 4, which is 2. And we are curious, is this equal to the square root of 36 over the square root of 9? Well, that's 6 over 3, which is 2 also. That works. Now, what you have to be careful of, what I'm about to write right now, do not copy this down, because this is not true. So a lot of people like to make this extension thinking, well, then the square root of the sum is the sum of the square roots. That is not true. And before you ever try to do something like this, accidentally, it might be wise to just try a couple of numbers and try a couple of nice square numbers that are perfect squares. And that means they have a nice square root. So that side works out to be 5. But if we did these separately, so if we were curious as to whether that's equal to the square root of 9 plus the square root of 16, is that equal? We get 3 plus 4, 7, not equal. Therefore, do not commit this to memory, but also don't make this mistake. So the first skill we're going to practice is simplifying square roots. So we need to call up this property we just demonstrated in the previous slide. And we also have to talk about what's called a perfect square. Now, so for example, 4 is a perfect square because we know its square root. So I'm going to put a table here of the first 10 numbers that have perfect square roots. So 1 is a perfect square, obviously, because the square root of 1 is 1. 4 is a perfect square because it's square root of 2, etc. So you can fill this table down here: square root of 6, 7, 8, 9, 10. These are, so the perfect squares themselves are things like 49, 64, but they're all quantities we have to be familiar with in order to carry out this next practice. So here's an example. The square root of 12, we don't know what that is exactly. It's obviously between 3 and 4, because the square root of 12 would be somewhere in between there, but we don't know the exact answer without using a calculator, and even then, it's only an approximate answer. So what we need to be able to do is simplify the square root, and this process has us rewrite 12 as the product of two numbers, two whole numbers, one of which is a perfect square. So now for example, 12 is 2 times 6, but I don't know either of those square roots. They're not in that table of perfect squares. So I look for another one and I think, well, 4 times 3. Okay, so now once we've acknowledged 12 is 4 times 3, we can use the property that the square root of the product is the product of the square roots. And why would we do that? Why does that simplify matters? Well, that's because we know that we know the answer to the square root of 4. It is 2. We do not know the answer to the square root of 3, so we leave it as is. And the answer, the simplifying square root of 12 results is equivalent to 2 rad 3. Let's practice this again. So 75, we look down our perfect square list, and 75, we find something that is divisible into 75. So I can see that 25, let's look at this one here, 25 goes into 75. So I rewrite this as 25 times 3, and I apply the property, and I know the answer to one of these. It's the square root of 25 is 5. I don't know what the square root of 3 is, but that's my simplified answer. So let's take something else, the square root of 80. So what comes to mind? Okay, so 10 times 8, that's no good because neither of those are perfect squares. But 4, I'm pretty sure 4 goes into that 20 times. And so I could rewrite that as square root of 4 times the square root of 20, which is 2 rad 20. Now the thing is, you have to be careful here because you're not actually finished. It turns out that 20 can also be simplified. The square root of 20 can be simplified. So we have to continue. Let me just we have to kind of do the process all over again. Sorry, trying to keep this as white. There we go, to be consistent. So now we're going to break square root of 20 down as square root of 4 times the square root of 5. And we know the square root of 4 is 2. Square root of 5. Notice everything's being multiplied together. So 2 times 2 is 4. That's square root of 5. And that's the simplified version. Now that's kind of a bit tedious. And could we have done better? Well, as it turns out, when simplifying radicals, it's important to find the largest perfect square that goes into the number. So 80 is actually divisible by 16. So if you have a calculator, you could test all the perfect squares and find the biggest one that goes in there. So that's the square root of 16 times the square root of 5, which is 4 rad 5, which you can see is a lot more efficient. So before we move on to further operations with square roots, I'd like to sort of teach you how to verify that you've simplified correctly. So the way to check is to basically undo the square roots by squaring both sides. So what does that mean? What is the square root of 12 squared? Well, you might already know the answer, but I'm going to write it out just to make sure you follow the reasoning. So square root of 12 squared is that product, and we know from the formula from before, but notice I've written it in reverse. So if I have the product of two square roots, it's just the square root of the product, and 12 times 12 is 144, but wait a minute, the square root of 144 is just 12. So in fact, I probably could have figured that out from the beginning, that the square root of 12, the whole point of square roots is it's what you multiply by itself to get back to the original number. So let's look at the right-hand side. So that squared is 2 rad 3 times 2 rad 3. And because that's all multiplication, even though we haven't written multiplication, it is really timesing. Everything is just multiplying together. I can rearrange the order of multiplication by the commutative property, and then I get 2 times 2 is 4, and rad 3 times rad 3, we have to recognize that now as just the same. Well, you could say it's rad 9, but maybe we could take a shortcut and just recognize that would be 3. So yes, 12 equals 12. So let's do that here. Maybe we can take some shortcuts now. So we know that rad 75 squared, they undo each other, they're inverse operations, that gives 75. Make sure that the other side gives 75. So you can take a little shortcut by just squaring each part. So 5 squared is 25, rad 3 squared is 3. Yes, that works. And one more time, just to confirm. Let's practice this one more time. The square root of 80 squared is just 80. Is that equal to 4 squared is 16. Rad 5 squared is 5. Yes, it works. And we're done. So now that we've learned how to simplify square root expressions, we can now begin to add and subtract. But I want to introduce you to a term which you may already know, you may have already heard. So square root is an example of a radical. There are other types of radicals. So if I write square root of 4, we know that's 2. But I could also write the cube root of 8. And that's the number that multiplies by itself 3 times to give it 8. These are both, even the nth root of something, they're all radical expressions. So square roots are a particular radical. That's just the basic root. Again, we don't write 2 there, but it's implied. So from this point on, I'm going to be talking about expressions. So I'm going to call this 5 rad 2 plus 3 rad 2. Just for simplicity. So if you get an expression like this, they're kind of, because rad 2 is the same in both, you can write this as 8 rad 2. It's like combining like terms. So if you had 5x plus 3x, then you have no problem saying that's 8x. So what about if we have something like this? Well, if we have different radicals there, we have to be careful because they're unlike terms. So it's really, you can't add 5x and 3y. So you can't do that. Not yet anyway, until you realize that rad 32 can be simplified as the square root. Let's see, the biggest perfect square that goes into that is 16 times 2. So we can write this as the square root of 16 is 4 rad 2. So 5 rad 2 plus 12 rad 2. Well, miraculously, they are like terms now, and we can write that as 17 rad 2. So you have to, that's why we need to learn to simplify so that we can combine like terms, even though it may not be obvious at first that they're like. So let's see, the square root of 20, that's 4 times 5. So 8 square root of 4 times square root of 5. Square root of 4 is 2. 2 times 8 is 16. Minus, now notice that sometimes I just go, instead of writing the first radical like I did here, I just go straight to the split version. So I can write rad 45 as rad 9 times rad 5, and that rad 9 is 3, and so that's minus 6 rad 5. And then we have the plus rad 5 kind of tagging along, hoping that it can be combined with the others, which it can, so that we get 11 rad 5 as the final answer. So now we're going to practice multiplying square roots, which we need this for again. So we've actually been doing some multiplying square roots already. We saw that the square root of 12 squared, for example, is just 12. And so we can, this is going to be pretty straightforward, but let's kind of deal with all eventualities. So the square root of 2 times the square root of 8 is the square root, or shall I say rad 16, and rad 16, that one, be prepared to be able to actually know the answer to a square, a simplifying or multiplying square root problem. So now 5 rad 6 times rad 2 would be 5. Let's use this property. We can write that as 5 rad 12. Now that's not your final answer. You have to be able to recognize when a radical can be simplified. So 12, remember, is rad 4 times rad 3. Or rad 4 is 2, so 5 times 2 times rad 3, and the answer is 10 rad 3. And now let's bring in, so I notice I'm bringing in extra numbers. We have that 6 and the 2 kind of hanging outside the radicals, so you can rearrange this once again. So that's 12 rad 3 times 15 is 45. So notice that rad 3 and rad 15 were not simplifiable by themselves, but you put them together and now you've got something that is. Rad 45 is rad 9 times rad 5. So 12 times 3 rad 5, which is 36 rad 5. So now we'll practice dividing square roots. So we're going to call up this property in reverse again. So if we have the quotient of 2 square roots, it's the same as the square root of the quotient. I'm going to take the problems that we multiplied the square root expressions in the previous slide, and we're just going to divide them. So we're working with the same numbers. Instead of multiplying, we're dividing. So let's practice this property. So we know that we can write this as the big old square root of 2 over 8. And what is a good idea is to simplify that first, so 1 over 4. And now I'm going to actually use the property in reverse just to break it apart, because these are easy to do. So the square root of 1 is 1 and the square root of 4 is 2. That's your final answer. And let's take this situation here. So the 5 is hanging outside, so that is not inside the radical sign, but I can write that as 6 over 2, which simplifies to rad 3, and that can't be simplified any further. And let's take the other radical expressions. This time we're dividing, and those on the outside can be, let's see, 2 goes into 6, that's 3 times, so that's valid. But be careful with the radicals. Don't start simplifying until you write it like this. Then you realize 3 goes into itself once, into 15 5 times, and 3 rad 1 is just 3, and then you have rad 5 on the denominator. Now I'm not going to circle this because we're not, well, I'll tell you what, I'll circle in red, because we actually have this thing in mathematics where we don't allow radicals to remain in the denominator for too long. So this answer isn't wrong. It's just we may not be able to add this to another expression unless we can rewrite it so that the radical is in the numerator. And this can be done, and this is what we're going to learn in the next slide. So in this last slide, we're going to learn how to get the radical expression out of the denominator by a process known as rationalizing the denominator. And the way it works is this. There's only one way to get rid of that radical in the denominator, and that is to multiply the quantity by itself. Let's see what that would do, because if we multiply rad b times rad b, you get back to b. That's what radicals do. And then you have to say to yourself, well, if I'm to multiply a fraction by anything, I have to multiply the numerator and the denominator by the same quantity. So we get left with a rad b over b in general. So let's just practice with the expression from the previous page. So rad 5 is the denominator, so we are going to multiply about rad 5 over rad 5, and that will leave us with 5 in the denominator and 3 rad 5 on the numerator. Now it's in a state that where it could be combined with other rad 5 expressions. Well, let's try this problem. So in this case, we multiply by rad 2 to the numerator and denominator. Let's bring this down, and we get 10 rad 2 over 2. That 2 goes into that 10 5 times, and our final answer is 6 rad 2. And now, to end with a fun one, let's have a look at this crazy expression. For the first fraction, we'll multiply by rad 2 over rad 2, and for the second, we'll multiply by rad 3 over rad 3. And that leaves us with 4 rad 6, let's correct that, over 2 minus 6 rad 6 over 3. And 2 goes into 4 twice, 3 into 6 twice, and 2 rad 6 minus 2 rad 6 is just 0. So you can take crazy expressions like that and probably never have imagined that those are in fact equivalent without being able to rationalize the denominator. So that brings us to the end of this video. If you enjoyed and you like my channel, please hit the subscribe button in the bottom right-hand corner. Thanks.